morning, everyone. I see I have my dedicated hecklers gallery right here in the front. That's awesome. So if you haven't been doing so, please go out and rate the talks of the speakers at Joined In. This one is at Joined In 15630. It's very important to us as speakers to get feedback to find out if we're doing what's right and what you like, or if we're not and how we can improve. It's also very important to conference organizers to find out what are the well-rated talks and what are not. Anyone who's been to one of my talks before knows that I like to give book recommendations at the very beginning. If you get nothing else out of this talk, get that these books are going to be very important to you in terms of your profession. The first one is called Patterns of Enterprise Application Architecture. Who has read this book? So here's a variation on the question. Who actually has a physical copy of this book? Dude, you are awesome. Right on, right on. So the important thing about this book is this. When you read it, you're going to discover that you're already doing a lot of the things that are described in the book. What's important is not that it tells you how to do stuff. What's important is that it gives you a vocabulary to describe the things that we're all already doing in some capacity or another. So if you have a class where all it does is move data into the database, and it only works with one table, and it moves information, data in and out of that one table, and then presents it right to the rest of your application, you could go through that description, or you could say, I'm using a table data gateway. We're going to be using some terms from this book today, things like active record, table data gateway, data mapper, things like that, table module. So that's Patterns of Enterprise Application Architecture. The other one is a little less well known, but it's also very important, or at least it was very important to me. It's called Scalable Internet Architectures by a guy named Theo Schlossnagel. I actually had the opportunity to work with this guy. He's genius. All they do all day long is build scalable apps to run at just gigantic scales for businesses. This is technically a talk on performance, but after a while, you're only going to be able to squeeze so much performance out of your system, and you're going to need to start scaling in a way to get even more performance out of it. So my name is Paul Jones. In a previous career, I used to get paid to be a spy. I spent 8 years in US Air Force intelligence, and I know that we all have our favorite military intelligence jokes now. Let's just assume that I've heard them one way or another. I've been programming both before and after that, though, since 1983. That's 30 some odd years now, which makes me, in a lot of ways, a very old man in this profession, in this field. More specifically, I've been programming exclusively, almost exclusively in PHP since 1999, and in that time, I've been everything from a junior developer to a VP of engineering. I've got a lot of open source code out there. The most recent big project is Aura. It is a collection of completely independent, fully decoupled libraries, so that when you download one package of this from Packagist, it has no other dependencies. If you want an SQL system, you download this one package, and that's all you get. If you want a query builder, you download the query builder package, that's all you get. And then you can wire them up any way you like in your application. And then based on top of Aura stuff, there's a new framework called Radar, which is based on which implements the action domain responder pattern. Action domain responder, for its part, is a refinement of model view controller. And it has some other libraries that uses Relay, which is a PSR7 middleware dispatcher. If you were at Matthew Ruffini's talks earlier, just before this one or earlier this week, you know what PSR7 is. Arbiter, again, is an implementation of action domain responder. I do a lot of framework interoperability group work. If you've heard of the coding standards, PSR1 and PSR2, I'm the person who shepherded those through the process. Also the PSR4 autoloader PSR, I'm the primary author behind that, along with a guy named Bo Simonson. The thing that I'm probably most well known for is modernizing legacy applications in PHP. If you've got a spaghetti mess of includes in your application, and it's globals everywhere, and you're afraid to touch one thing over here because something else over here breaks, this book will give you a step-by-step process to improve the quality of your application and keep it running the whole time so that you end up with a much higher quality application at the end of it. Again, it's a very detailed step-by-step process. If you're interested in that kind of thing, come talk to me afterwards. So today's talk is about the N+1 problem. We're going to lead into it by talking about performance and benchmarking. You know, how do we measure the performance of our applications? And in doing so, what are some of the things that drag down the performance of our application? One of the things that drags down the performance is the N+1 problem. We'll talk about what it is and how to recognize it. Then we'll talk about some solutions to the problem that we can write ourselves by hand. And then we'll talk about some ways of automating that problem, or automating the solution to that problem. So the first thing we need to talk about then, because it's a performance talk, is performance benchmarking. We all hear about benchmarking all the time. One of the things that we need to point out, though, is that there are lots of different things that we can benchmark. We can see how much CPU time is being used. We can see how much memory is being used and benchmark that. We can see how much disk access is being performed, whether we're doing a lot of database connections or not, whether we're hitting the network a lot, how many requests per second we're able to deliver with our web applications, things like that. The way you do benchmarking, and I'll talk about this a little bit more, is you benchmark the system, you measure its performance, then you change one thing, and then you measure your performance after the change. The idea is to make one isolated change so that you know this one thing caused the performance to change in such and such a way, either to make it better or worse. These things on the left-hand side, then, are things that are very easily measured. They're very quantifiable things. But I often hear a lot of people say, well, I don't care about that so much. I want to measure my developer productivity. I want to measure how long it takes me to implement something quickly, how long it takes to add a new major feature. I want to benchmark how long it takes me to fix bugs. Those are probably not the proper subjects for benchmarking measures, because it's very hard to control for variability in those things. It's very hard to start, say if you're measuring how long it takes to add a feature, to start in one place and then add the feature and then measure how long it took, and then add another feature and measure how long that second one took and see what the difference is, because there's a lot of other variability in there. If you were going to measure that, you wouldn't know if you were actually, you don't know what you're actually measuring there. Is it the familiarity of the programmer with the particular problem? Is it the particular tools that developer used in solving that problem? So on and so on. So these things on the right, while they are good information, they are not the proper subjects of benchmarking. With that in mind, then, we're going to do benchmarking of an app. We're going to talk about how to benchmark an application just in its barest state. We're going to do so in terms of requests per second. Of course, it's not enough to just benchmark the application. As Dirty Harry tells us, a man's got to know his limitations, and it turns out that there are lots of different limitations in the system that we need to figure out. We need to figure out how fast the hardware itself is capable of responding. What is it able to do just by itself? And then we're going to add the operating system on top of that. How long will that, how does that reduce our performance by adding on this extra work that happens? Then we'll add on the web server. How much performance drain comes from just adding on a web server, and then tacking on the language, and then tacking on a framework, and tacking on an application. We're not going to go through all of these steps. I've got an entire other talk about benchmarking. The point is that we need to benchmark different layers of what's going on so that when we discover our performance is not what it needs to be, that we will be able to figure out more accurately where to expend effort in improving the performance. If it turns out, for example, that we need to get 500 requests per second out of our application, but the web server itself is only capable of delivering 300 requests per second, there is no amount of work you can do in the application to make it go faster. The web server has a hard constraint on it. That's what we're going to figure out here. We're going to see it going stepwise. Does everyone get where I'm coming from there? I see some nodding. Okay, good. So what we're going to do is we're going to start a little higher in the stack. We're going to measure the performance of just a web server. We're just going to see how long it takes to how many requests per second a web server can deliver of just plain old indexed HTML. We're going to do this on a stock Ubuntu server, on stock Amazon EC2 Large, using a stock installation of PHP and a stock installation of MySQL. The point here is that when we do benchmarking, we want to have replicatable results so that other people can set this stuff up and see if they get the same results. And if they do, then we know the benchmark is accurate. And if they don't, then we know there's some variability that we haven't accounted for. So again, these numbers that we're going to see, these are on stock installations. The first thing we're going to do is we're going to benchmark how many requests per second this stock installation, how many requests per second it can deliver in terms of just plain old static index.html. After we benchmark that, we have now found the fastest possible speed that this server will operate at for us. Then we're going to tack on the language. We're going to benchmark an index.php script where all it does is echo hello world. The point here is to find out, by adding in the language, how many fewer requests per second do we get just by adding on the language. Then we're going to put in two things. We're going to do one benchmark of MySQL Connect. And yes, I know MySQL has been deprecated, but you got to remember I'm used to dealing with legacy applications. There's a lot of stuff out there still using this. We're also going to do a benchmark of PDO just by connecting to the database. We're not going to do any queries or anything at this point. We're just going to see what does it cost us in terms of requests per second to connect to the database. What performance implication does that have? Then after that, we're going to do a connection, query, and fetch on a very simple table to see what the costs of doing a very basic fetch are. And again, the idea here is to figure out what are the outer limits of our performance capacities. So in that Ubuntu, that stock installation of PHP, when you run a benchmark, when you run something like Siege or Apache Benchmark or HTTPerf against it, what we discover is that plain old index.html delivers, you can get 2,700 requests per second out of that, which is pretty good, right? But that's the absolute outer limit of performance on this system right now. If you need something that delivers 3,000 requests per second, this system is not going to do it. You already know that there's no amount of effort you can spend improving your application because it will never go faster than this. Similarly, when we add PHP and just have it echo hello world, performance drops by about 25%. Now again, this is not terrible performance. We're still seeing 2,000, 2,100 requests per second. The point is that by adding something in, we see what the performance drop is. So again, if we've got a PHP application that needs to deliver 3,000 requests per second, there's nothing we can do in this system to get that. We already know that we have to scale across multiple servers. So now that we've got some baseline performance measures in place, we know that in fact, let me back up for a moment. We're going to be talking in terms of relative percentages. So in PHP here is like 1. It is the base relative percentage that we're talking about. It's 100%. Everything will be expressed in terms of being percentage faster or percentage slower than that. So let's do a MySQL connection. We write a very little bit of code. We set up our connection information, and we say MySQL connect, select the database, and then we're going to echo something, because if we don't echo something, we're just going to see white screen. We don't know if it's succeeded or not. So we echo, yes, we've connected, everything's fine, there weren't any errors. So that's what the MySQL connection script looks like. This is what the PDO connection script looks like. Again, it's very similar. We just instantiate PDO, and by instantiating PDO, it makes a connection, and we echo, we connected. There weren't any errors. So when we do these two things, and we bench, and this is the only thing that changes. All we've done is changed echo hello world to one of these two things, either a MySQL connect or a PDO connect, and we run exactly the same benchmarking run. What we discover is that when we, just by connecting MySQL, we lose about 20% performance, just by connecting. Now again, these are, the MySQL server in this case is on the same server as PHP, so we're not actually incurring any network costs here. This may not be the way you want to do stuff. That's going to have a different effect on number of requests per second. If you wanted to connect across the network, you could do that. I just want to be clear about what's going on here. On the same server, we're losing about 20% in terms of requests per second. It's about the same for PDO. It's actually a little bit, we're a little bit better off. It's like 18%, something like that. Does everyone see what's going on here? So the mere fact of connecting to the database causes a performance hit. Again, maybe this is not so awful. It's 1,800 requests per second. That's going to be just absolutely fantastic for most everything. But if you know that you need 2,500 requests per second out of your application, you know that you can never ever connect to the database now. It simply won't be able to respond in the way you want it to, or you're going to have to start scaling. So that's the drop-off merely from making a connection. Now let's actually do a query, and what we'll do is we're going to create the simplest possible table. It's hello, and we're going to insert however many rows that is, one character each for hello world, exclamation point. And then we're going to select all of these rows and echo them out. So this is the database table that we're using. This is what the MySQL query and fetch looks like. We make the connection, we query against the rows to get everything back, and then we echo out each individual row and the one character that's in it. Same thing for PDO. PDO, we make the connection, we execute the statement, we fetch everything, and we echo out each character. When we do this, this is what the performance implication is. So we have dropped from originally, and let's just look at PDO, 2,700 requests per second. Making the connection drops us to 2,100, or invoking PHP drops us to 2,100. Connecting to the database drops us to 1,800. And doing this super simple query drops us another 10 percentage points, down to 1,600. Pretty much the same thing for MySQL. Now again, these are fantastic numbers. This is really good. But again, this is the most basic thing you can do with a database connection. The point here is to say that just by connecting to the database, you're losing roughly 27 percentage points in performance. Does everyone see? So we need to pay attention to these performance issues The database especially is a point of contention here. We need to make sure that whatever interactions we do with the database are as minimal as possible, they're as efficient as possible, because this can be a real performance drain. And looking at numbers is boring. This is what the graph looks like. And this is much more dramatic. We can see what the drop-off is. Which brings us to the N+1 problem. Who here has heard of the N+1 problem before? A few people, that's good. For everyone else, I'm going to lead into this by way of a story. The reason I started paying attention to this was that at a previous employer, they had a performance, there was a report that they would run every once in a while. The clients would have to run. It was taking 3 hours to finish. So the client would start it, and then it would run for like 3 hours, and then maybe it would finish, and maybe it wouldn't. They would get a white screen of death, or it would say, query terminate, or connection terminated, the query ran out of time, something like that. So they assigned me to try and fix the problem. Why is it taking this long? When I dove into the problem, I realized that what was happening was they were trying to select 2 million rows out of the database and marshal those 2 million rows into 40,000 record objects. Those record objects were then processed to generate the report that was delivered in HTML. When you're trying to solve that kind of problem, and it takes 3 hours for each iteration, that's kind of terrible. You do not want to make a change and then wait 3 hours to see if it works or not. So the first thing I did was I reduced the data set to 2,000 rows and 40 record objects, and then ran the same thing. Just reduce the data set so you're getting a smaller amount of information out of it, so you can have a faster iteration time. And then I looked at the profiler after it did everything it was doing, and I realized that the application was making 201 queries in order to select these 2,000 rows and create these 40 row objects. In fact, what was happening was there was one master record, and there were 5 relationships on each record. So for the one record, we would do one select, or for the master set, there was one select, and then for each record in that list, it was doing an additional 5 selects. So if you've got 40 record objects, that's one select to get the first 40. And if there's 5 relationships, that's 200 more queries, one for each relationship on each record in a loop. Everyone see what's going on there? That's terrible performance. That's the N+1 problem. So the the 1 is the master set of records, and the N is the exponential number of queries that have to happen in order to fetch all of the related information. This is what it looks like in PHP. So for the examples here, we're going to be talking about the canonical blog post example, where we've got posts and comments, maybe some metadata on the posts, that kind of thing. So we do one query. If we want to get 10 posts, we do one query, we get the first 10, and now we've got an array of all of those 10 posts. But then to get the comments, we loop through each post, we get its ID, we make a query against the database to get its comments, and then we put them into the posts array so that the posts have all their comments attached to them. That's the N version. So how many queries are going on here? A total of 11. One query to get the first 10, one query to get the master set of 10 records, and then one query for each of the 10 records to get all the related information. If we needed 2 pieces of related information, this would be 21 queries. One for the master set, 10 queries for the first piece of related information, and 10 queries for the second piece of related information. Oh, it seems to have gone off the top a little. This is what the data structure looks like that comes back in this case. We're going to be referring back to this over and over again. The idea is that we've got this master posts array. Each top level element here is a blog post of some sort, and then there is a comments element on each blog post that carries the comments that are attached to the post. So why is this a problem? Well, obviously it's a big performance problem. Each relationship is one additional query. If you've got 5 additional relationships, that's 5 queries per master row. If you've got 10 records in that case, that means 50 additional queries. 50 times you're going back and forth to the database. And again, remembering the performance numbers that we saw at the beginning, each one of those causes a 10% performance hit. It's very, very quickly you drop to next to 0 performance. It's terrible. In the case of 40,000 records, the original example where it was taking 3 hours, you remember I had reduced the data set, so it was only 201 queries. But on the full data set of 2 million records, that is 200,000, technically 200,001 queries being performed. No wonder it's taking 3 hours. This is a terrible performance problem. How can we take care of this? Well, the only way to take care of it is to use fewer queries. But how do we do that? So before we talk about the solution to this, I want to talk about what leads us into doing things this way in the first place. Why does the N+1 problem occur to begin with? And I'm going to assert that it is because we as developers have a cruddy mindset. That is, when we think about these applications, we think in terms of individual records. We're going to create a record, read one, update one, delete one. One. We're always thinking in terms of one. We have this individual record-oriented focus, which is fine, depending on what you're doing, but it leads us into using patterns like active record and row data gateway. Again, these are perfectly fine patterns if you know what they're well suited for. The point here is, though, that we treat collections of records, multiple records being fetched all at once, we treat that as a secondary case, not as a primary case. And then when we get in a hurry, because we say, well, we'll deal with individual records, and then we'll deal with collections of stuff later. But later never comes. Later is always a problem. There's never time. So we get in a hurry, and instead of treating collections as a first-class problem, we treat them just as a collection of individual records that are being put together, instead of as a set of records that are grabbed all at once. So we end up doing things in loops this way, because when we build one record, we build that one record in a loop. Well, we'll just build all of these records in a bunch of little loops. Then we see this N+1 performance problem. So the beginning to fixing the N+1 problem is not in code. The beginning of fixing this problem is changing your mindset. Now, I'm going to argue that what you need to do is change your mindset from crud to bread. Bread is nice. It's crusty. It's warm. It's fulfilling. We like this. It's almost identical to CRUD, except we add one additional thing, and that is browsing an entire collection of stuff. So instead of create, read, update, delete, it's browse, read, edit, add, delete. The last four are the same thing. The first one, though, is a collection of records. And notice that it's the very first one. We start by thinking, how do we create a bunch of records all at once in an efficient way? Browsing is a first-class requirement in this case. And because it is a first-class requirement, because we're starting with this, it leads us to different patterns out of the book that I talked about earlier, Patterns of Enterprise Application Architecture. Leads us things like table module, table data gateway, perhaps data mapper if you feel like that kind of thing. We start building collections of records as our first use case, not individual ones. And in doing so, we learn that efficient building of a collection of records leads us to efficient building of a single record. A single record is just a case of a collection where there is one record in the collection. The opposite is not true. It is not very easy to efficiently build a single record and scale that out to building a lot of records all at once. So by treating collections as a first-class problem, by changing your mindset there, that is the beginning of solving the N+1 problem. We're going to talk about two solutions in code then. Once we get to the idea that we want to build a bunch of records all at once in an effective way, how do we do it? There's two ways. We're going to talk about this one called the single query solution and another one called the query and stitch solution here in a moment. So the single query solution is this. The idea is that instead of selecting the master set and then doing one query for each record in the master set and for each relationship in the master set, we're going to figure out what all the relationships are for everything all at once, and we're going to select everything in a single query statement that goes out to the database. So we end up making one query to get all the information we need, both for the master set of records and for all the related sets of information. Once we've got that back, we're going to loop through that set of data, and we're going to marshal the data into individual records and pick it apart as we go. What that looks like in PHP is this. So we're going to start with a one-to-one relationship here, where we've got a posts table, and we've also got a statistics table that counts how many times how many times the post has been read, how many people have commented, like a summaries table kind of thing. So we select from posts. We're going to also select the statistical hit count from this with a left join. We're going to get all of those rows back all at once. We're going to loop through them. So we can see that we go through the rows, and each row is a post. And then we're going to pick out the hit count column, and we're just going to put it in a different place in the array. That way, all that information that came back as a single row is now split into several portions within the post array so that we know that it came from some other table. And when we send it back to the database, we know that this information is not actually part of the post. It's actually part of a different table, and we can handle it differently. So this should be very straightforward. Does anyone not see what's going on here? This should be pretty simple. That's a very simple case. This is the more complex one. This is what we were talking about earlier with comments. In a one-to-many situation, it's a little bit different. What we're going to do is we're first going to start out by selecting all the posts, and then all the comments on those posts in one go and get them back. But here's the problem. When we get them back, what we're going to see is a lot of repeated information because of the way SQL works. What we're going to see is the first post, let's say there's 10 posts, and each post has 10 comments. We're not going to get back 10 rows, we're going to get back 100 rows because we've got 10 posts, and that's going to be repeated 10 times, and then each of those repetitions is going to have a different comment on it because of the way the joins work. So what we're going to have to do is loop through these to get a post out and then figure out if we've already got the post or not, and then if we don't have the comment yet, we can attach it to the post. What that looks like is this. So we get the post, we've done this query, we've gotten back this set of 100 rows. We're going to loop through them. We're going to see what the post ID is on the current row that I am processing. If I don't have that row ID yet in my posts array, we're going to create an entry for it, and we're going to key on the post ID in that array so that we can look it up later very easily. We're going to keep the ID, we're going to keep the title and all the other stuff that relates to that particular post. That's what happens if it's not already set. If it is already set, that means that we're looking at a repetition on that row for the post. We don't need to deal with it again. We can then go on and look at the comment portion of that row and say for this post ID that I've got right now, go to the comments element on that post and add the comment that I'm looking at on this row to the post for the post ID that I'm dealing with on this row. It's a little more complex. Does anyone have questions about this? Again, it's pretty straightforward. You're just looping through the row and you're looking for repeated stuff. Yes?
You're talking about a large data set. Don't you say or don't you feel like the usage of arrays is going to be a performance hit there?
If you have a very large data set, don't you feel like using arrays is going to be a performance, or more specifically, a memory problem in this if you have a very large data set? The answer is yes. We're going to talk in a little bit why I don't like this solution in most cases. But this is where a lot of people start. And it is valid in some cases, so I want to make sure that it's pointed out. Other questions before we continue? Okay, so I actually tricked you a little bit. There's something else going on here, and that is I want you to look at what's going on here. Select posts and comments, but the original example that I gave was to select the top 10 posts, the most recent 10 posts. Select limit 10. What happens if we put a limit 10 on this? We get the first 10 rows, but we don't necessarily get the first 10 posts. Again, remember, we're dealing with SQL here. It's just going to give us back rows. It has no idea that we're going to be turning these into records later. So if you've got 10 posts, each with 10 comments on them, selecting all gets you 100, but selecting with a limit 10, you're not really quite sure what you're going to get back, even if you order things properly, because there's no way to remove the repetition of the rows for each comment. So there's a problem here, and that is this is very difficult to do limits on in a one-to-many situation. Which means that single query is good in one-to-one situations, but it's maybe not so great in one-to-many situations unless you want to grab all of the data all at once. So what happens is, again, we loop through the result set to marshal the results into our domain objects. It's fine when we have one-to-one, but one-to-many turns out to be really difficult. Not only because we've got all this repetition, and we've got all that complexity associated with it, it means that if we add a third relationship, now we need to check for repetition not only on the master set. We also need to check for repetition on the first set of related data, and then the second set of related data is always going to be unique. If you add a third relationship, though, now you need to check for repetition on the master, the first related set, the second related set, and the third set will always be unique. As you add things on, this becomes more and more difficult to deal with. That result set also gets larger and much more repetitive. Like Michelangelo said, if you end up with a really large result set, if you've got, again, if we're in that 40,000 record objects scenario, you're going to be getting millions and millions of rows back, and you have to loop through all of them. That's going to be really tough to deal with, especially when you're talking about the repetition. And finally, it's extremely difficult to do a limit offset with this. So while I like single query for some limited situations, it is not my favorite solution to the N+1 problem. My favorite solution to the N+1 problem is what is called the query and stitch solution. I see other names for this. This is the name that I like. Query and stitch solution works like this. We're still going, so let's back up. In the original N+1 problem, we've got one query for the master set of records, and then one query per record per relationship. In this, we're still going to, and then in the single query solution, we've just got one query no matter how many records we've got, no matter how many relationships we've got. This is a middle ground. What we're going to do is we're going to have one query for the master set of records, and then one query for each relationship, but we're going to get back all of the data for all of that master set of records in one go, so that we end up having only one query per relationship, not one query per record per relationship. So this is not exponential, this is linear. We're going to do a query for the related set. For each related set of information that we pull back, we're going to loop through it. We're going to put that information in, we're going to take that related information and put it in the master set. Then we're going to go on to the next relationship and stitch them all in. What that looks like is this. So we're going to do our first query to get the top 10 posts. And notice we can use a limit again now. We just want the top 10 posts, so we can use our limit statement here. What we're going to do, though, is we're going to loop through this the first time, and we're going to key an array on the ID of each post. Again, the reason we're doing this is so that we can very quickly find, just by array key lookups, what comment gets attached to what post, because the comment knows what post ID it's supposed to be associated with. So this gets us the master set of records. We then go through and get all of the comments for all of those posts all in one go. So what we do is we build this statement. We're going to have a placeholder in there for this list of post IDs that we're going to do. We're using an in clause here because it's very easy to work with. We're going to bind that list of post IDs by getting the array keys of the posts that we just looped through back here. Again, we went through the rows, we found the ID, and we keyed the posts on that ID. We can now just get the array keys out of there, and that tells us all the post IDs that we need to select for. Then we go select all of them. So if the database has 10 posts in it, and there are 10 comments for each post, we're going to get back 100 comments here. The next thing we have to do is loop through those 100 comments, find their post ID, and attach them to the right post. And that's very simple. Go through all the rows. We're going to treat it as a comment name. We're going to find the ID that it should be attached to. And from the posts with that ID, the comments element, we're going to say add this comment array to it. Add this comment array to it. That's it. That's the query and stitch solution. It's a lot easier than the single query solution. Now, I want to point out that we are adding on one additional loop. We're not doing one query, we're doing two. And we're adding this one additional loop by looping through the posts in the first place and then looping through the comments. But instead of doing 11 queries to get our 10 posts with all the comments, instead of doing 11 queries, we're only doing 2. That's where the subtitle comes from. A stitch in time saves 9. By stitching these things in, we can get all of our related data all in one go and then come back and stitch it in a loop. It's very easy to do a limit offset, unlike with the single query solution. It's also very easy to add multiple related sets of information. So we've got our posts, we've got our comments. That's going to be 2 queries. If we additionally have statistical information that we want to add on, we do one additional query to get all of the statistical information for all of the posts and one additional loop to stitch the stats information into the posts. So we end up with a total of 3 queries. Again, this is a linear expansion and not an exponential expansion. It's very easy to do. Now, right now, some people are thinking, well, wait a minute, I thought loops were bad. I thought you said at the beginning, we're not supposed to be doing these loops. That's the cause of the performance problem. No. The doing of queries inside loops is the source of the performance problem. So the performance result of this is originally we had 40,000 records being generated from 2 million rows, 200,001 queries, because there were 5 related pieces of information. We have, under the query and stitch solution, we go from 200,001 queries to 6. And in doing so, I measured this, that report went from taking 3 hours, if it ever finished at all, to about 5 minutes, a little less than 5 minutes. Now, 5 minutes is not fantastic. 5 minutes in in the web world is still not really great. But if you're the client and it goes from 3 hours to 5 minutes, you are super, super happy. We were able to actually to increase performance past this. But what is that, a 60 times difference, something like that? Just by thinking in terms of collections of stuff, rather than thinking in terms of individual records. Any questions on any of that? So that's how you do it in native PHP. You do that once, it's cool. You do that twice, it's cool. The third time, you start figuring out, maybe there ought to be a way to automate this. How can I take away the having to write the loops and write all the individual queries myself and stitch all that stuff in myself and just basically give something some data and let it wire things up for me? The classical answer here is to use an object relational management system, use an ORM of some sort. And in fact, that's what's going on under the hood of, if not all of them, then most of them. When you ask for an eager fetch or a with include or an include related set of information, that's what's going on under the hood in these object relational management systems. The problem is that not all projects are necessarily amenable to an ORM, either because the project is legacy or because there are other problems, maybe we don't want to bring them in. Not least of which because ORMs are really strongly disliked by a non-trivial set of developers. How many people here, let's listen carefully, actually like using an ORM in a legacy application? Not a lot. I've written ORMs. There are times when they are awesome. And there are times when they're not necessarily a great fit. So that I say this as someone who has written them, who uses them, who has a love for them in their place, but sometimes there's no place for them. And the time when there's no place for them, and the thing is that people don't like them for what I will call valid reasons. First of all, there's the overhead of including and learning the thing in the first place. Who here has used Doctrine before, or uses Doctrine? How many lines of code in that? How many millions? Bigger than, it's at least half the size of the entire Zend framework. I mean, it's gigantic. It's got lots of stuff in there. And then in addition to including it and having to be responsible for everything that's going on there in your project, you also need to learn how to use the silly thing, which means learning this non-SQL dialect or a pseudo-SQL dialect in a lot of cases, either by writing text that looks like SQL but isn't, and that gets translated to SQL somehow, or by setting properties on a query object or calling methods on a query object. Again, these things can be benefits or they can be drawbacks. A lot of people don't like them. DBAs in particular, or at least the DBAs that I have worked with in particular, are not especially fans of ORMs because these ORMs are sort of opaque. They have funny behaviors under the hood doing what they think they ought to do in order to optimize your query for you, which makes it not only difficult to hand-tune, but it makes it very difficult to figure out why in this particular edge case it's behaving one way when it behaves in a different way all the rest of the time. So it can be ineffective and unpredictable in certain edge cases, and then it can be a resource hog when it's doing it. And finally, we're trying to avoid N+1 in the first place. If your ORM supports lazy loading, and you get what you think is all of the information you need from your domain layer, and you pass that persistence object out to your view, and your view presents it in a loop and just accidentally happens to ask for a property on that entity that has not been fetched yet, it's now going to go back to the database every time it goes through that loop, and we've got our N+1 problem back again. So again, there's a place for ORMs. Sometimes it's useful, sometimes it's not. These are some of the cases where it's not useful. But it turns out that in this particular problem, the N+1 problem, if you've got existing code, and you've got this trouble, you've got this N+1 problem, you need a way to automate away the solution. The problem for you is not writing the SQL. The SQL is pretty easy. We already know how to do that. We know how to get all the records we need. The problem is wiring up these objects, automating away those loops and the stitching together of stuff. So it's the problem of marshalling these result sets into our domain objects. When I first ran into this problem in the 3-hour report scenario that I talked about, after I went through that, I sat down and I wrote a package called aura.marshal. And the only thing that aura.marshal does is this wiring together of the objects, this stitching together of result sets into our domain objects. It doesn't do queries of any sort. In fact, you can use any data source that you want with it. You can use Mongo, Redis, CSV, XML, SQL. What happens is you fetch the data. Actually, let me back up. What happens is you tell aura.marshal, how should my objects be wired up? What properties relate to each other so that they know how to get stitched together? And then you feed it result sets from whatever data source you want. And then you ask the marshal, give me back a particular record. And it will do all the wiring up for you based on the data you have already fed it. What that looks like is this. So first of all, we've got this idea of types in Marshal. These would be your entities, your domain, probably maybe your domain aggregates, maybe not, depending on how you feel about them. But we've got this Aura Marshal manager, and we tell it there's a particular type. We're going to call it our posts type, because it's blog posts. It has its identity field is the ID field. It relates to comments in a has-many relationship. The native field on the post is post.id. And the foreign field on the comments relationship is the post_ID field. And then we have the reverse of, or the reverse of the relationship. I'm not sure if it's the reverse or the obverse. Where we have a type called comments. Comments has its own identity field, and it has relationships back to the post based on a particular foreign type. It's the post type. It belongs to that type on a particular field, a particular native field, and it relates to a particular remote or foreign field. So once we set up those types, you would do that for each type in your system. So if you've got 50 types, you're going to have 50 entries of that sort with all of their relationships defined therein. But in our posts and comments example, we do pretty much the same thing as we were doing before. We just are able to get rid of the loops now. So we select all our posts. We feed them into the manager. We say, manager, post, load this result set for us. And what we get back from the manager is all of the IDs that were just inserted, because it knows what the identity field is. It gives those back to us so that we can use that information in the next query that we're going to run. In this case, the next query we run is to get all of the comments for all those post IDs. So select star from comments where post ID is in this list of post IDs, bind it in, fetch all the results, and then we say, manager, I want to load up all of the comments with this result set. So we've done 2 queries now. We haven't done any wiring of our own. But because we did that set type stuff earlier where we told it this is how the objects get wired up, we can say, manager, give me all of the posts, loop through them. Here's the post title, and all those rows that were arrays are now objects. The post title, it has this count of post comments, because post comments is an array underneath that. We've got access to all this stuff. It wires it up for us automatically so that we don't have to do that stitching portion. All we have to do is the queries. So in conclusion, we have looked at performance benchmarking, why performance benchmarking is important as a way of figuring out where the limitations are in our system. One of okay. So why that's important. Why N+1 then, in relation to that, is a particular kind of performance problem. How to identify it, what it means. How we get there, because we're thinking about individual records instead of groups of records. And then some solutions we can use in native PHP to take care of this for ourselves, either in single query situation, either in a single query approach, or my preferred approach, the query and stitch approach. And or a Marshall as one way of automating that, not necessarily in terms of the queries, but in terms of wiring up the domain objects for us, so that we can remain in full control of the SQL queries that we write. I actually have a book about this. There are a few more, you have essentially heard the full contents of the book. But if you want some more information, how to deal with many relationships, and other kinds of relationships, how to go through your logs and look for telltale signs of this kind of thing, go out to leanpub.com, SN1 PHP, solving the N+1 problem in PHP. And again, please go out and rate this talk. That's all I've got. Thank you very much for your time. Questions or comments before we continue? Or questions? Yeah, please. So I heard the first part of it. I'm going to guess what the rest of it was because I've heard this before. Tell me if I get this wrong. We're using the in. Is this the right one? Yeah, we're using the in operator here. We have been told that the in operator is bad for various reasons, that it doesn't use indexes. In modern, how long have you been working with MySQL? 15 years. So me too, by the way. It's been a long time. That's no longer the case. In the more modern versions, in fact, Morgan Talker may be around here someplace. All that kind of stuff is no longer a problem. And it hasn't been a problem for 3 or 4 years anyway. Talk to Morgan about that one. The variation on this is maybe you want to do a join if it's a really large set. And following that, so one of the other questions that I hear in relation to this is, if you've got 100 IDs, isn't that going to be a really long query to send across the wire? Will MySQL be able to accept a query of that length? Well, even if it's 100 IDs and they're all 3 digits, that's 300 times, I don't know how many bytes that would be. It turns out to be very small. So the question then becomes, how many elements can you put in an in clause? And the answer to that question is a whole lot. Again, for data sets under 1,000, this is probably not going to be a problem for you. Other questions? Yes.
What's the practical limit of this? Like you said, that's 13,000. What's the upper limit of the algorithm you're talking about?
So what's the upper limit of the algorithm on this? That's actually a very complicated question, believe it or not. There's an upper limit on everything. If you have 100 pieces of related information that you need to get coming back on 1 million rows, your performance is probably not going to be great anyway. This is going to be better. This is still going to be orders of magnitude better than 1 query per record per relationship. So I hate to say this. The answer is it depends. As you add data, obviously it's going to slow down. But the slowdown on this is going to be linear rather than exponential. And that's the thing we're looking for. And again, the follow-on to that is, well, if you're pulling 100 sets of related information or you're pulling 10 million rows at a shot, why are you doing that? Are there perhaps other ways that we can deliver value to our clients in a way that also keeps the performance up? So again, there are limitations to everything, and there is a limitation to this. The only thing that I will say is that the boundary on this is much further out than the boundary on the N+1 solution. Other questions? Anyone? Anyone? Bueller? All right. Thank you very much for your time.